Hi, I'm Jim. Here I'm going to introduce dye-sensitized solar cell fabrication and some solar cell tests to you. Dye-sensitized solar cell is also called DSSC for short. It has a very simple sandwich structure with electrolytes in the middle. The top electrode is platinum nanoparticles on the surface of FTO glass, and the bottom electrode is titanium dioxide nanoparticles loaded with dyes on top of the FTO glass. Here shows the working mechanism of DSSC. When the photons hit dyes, electrons will be excited from the HOMO to LUMO in the dyes. Then the excited electrons will inject to titanium dioxide, while the oxidized dye will be reduced by the redox couple in the electrolytes. Okay, let's start fabricate DSSC. Here is an FTO glass. FTO is short for fluorine doped tin oxide, a transparent conducting oxide. Only one side of this glass is coated with FTO, which is the side we need, and we use millimeter to tell which side is with FTO, because FTO is conductive while the glass is insulative. This side is conductive, conductive, and conductive. And then we'll turn the glass over and use a diamond cutter to mark on the glass side. As you can see, there's a number on the glass side. Here is the jeweler. We usually drill 2 holes on the FTO glass for electrolyte injection. And we fill the container with water to prevent glass dust splashing out. We put the FTO glass in the water. And then we start to drill it. This FTO will be spattered with platinum nanoparticles on it, which is the contour electrode. Okay, here we get it. And then I'm going to prepare a tape with hole for the titanium dioxide paste braiding. We get the magic tape attached to the perfume, and then we start to make a hole on it. One, another one. Okay, we get it. Okay, here is the cleaned FTO glass. And then I'm going to adhere the magic tape on the FTO glass. The magic tape is with a hole in the middle. I'm going to fabricate 2 DSSC. And then I'm going to use the blade to make the tape adhere to the FTO glass tightly. This one is done. I repeat the same procedure for the other active gas. Use the blade. Here we have the titanium dioxide nanoparticle paste. It is composed of 30 nanometers titanium dioxide nanoparticles, ethanol, ethyl cellulose, and butanol. And we applied a portion of paste on the tape. The same for the other. And then we use the blade, the glass blade, to spread the paste across the plate with the support of the adhesive tapes on the active glass. I repeat the operation 3 times to get a homogeneous layer. And the same for the other one. First time. And the second time. The last time. But the film is not homogeneous enough, so I do it once more. Okay, I'm going to transfer the samples to anneal at 150 degrees Celsius for 10 minutes. After the samples are cooling down, I will repeat blade coating with the paste. The paste is composed with 30 nanometers titanium dioxide nanoparticles. Apply a portion of the paste on the tape and use the glass blade to coat. Repeat 3 times to get a homogeneous layer. First time. The second. Last time. Okay. Do the same for the other one. Later on, I will show you the SEM image of the titanium dioxide. And then we transfer the samples to anneal for another 10 minutes at 150 degrees Celsius. After 10 minutes, we fetch the samples and wait the samples to cool to room temperature. Then I'll repeat plate coating with the paste composed of 200 nanometers titanium dioxide nanoparticles. This paste is different from the previous one because the size of the titanium dioxide nanoparticles. This paste is for the scatter layer. Apply a portion of the paste to the tape. And then use the glass plate to coat it. And here we get a homogeneous layer. This one also repeats 3 times. So all in all, we have 2 transparent layers and 1 scatter layer. The transparent layer is composed of the 30 nanometers titanium dioxide, and the scatter layer is composed of 200 nanometers titanium dioxide. Okay, and then we transfer the samples to the hot plates to anneal for 10 minutes. Here we have completed the plate coating of the titanium dioxide paste. I'm going to remove the tape so that I can increase the temperature higher to 480 degrees Celsius gradually. And the other one. Tape adhere to the FTO glass very tightly. The temperature will increase 55 degrees Celsius per 5 minutes, and the temperature will reach 480 degrees Celsius finally. The samples will anneal for 45 minutes at 480 degrees Celsius. While the samples are annealing, let's see the SEM image of the transparent layer and scatter layer. The transparent layer has a larger surface area to volume ratio so that it can be loaded with more dyes. And the network with 200 nanometers titanium dioxide, which is the scatter layer. This layer can scatter the light more effectively. Here shows the cross-section of 2 transparent layers. Each layer is about 3.5 micrometers. Here is the dye solution. We will immerse the annealed samples to the dye solution. And the titanium dioxide network will be immersed in the dye solution for about 15 hours. Made the samples backside to backside. Expose the titanium dioxide network outside. Put them in. That's not good. Adjust a little bit. Okay. I'll put the a solution in the dark. By now, we have fabricated the titanium dioxide nanoparticles on top of the FTO glass. And we will continue to fabricate the counter electrode, which is platinum nanoparticles on top of the FTO glass. Here is the stage where we put the samples on, and here is the platinum target. It goes the chamber. And I start to pump the chamber. Here shows the pressure of the chamber, and here shows the sputter current. Adjust the argon gas flow. Now the chamber pressure has reached a standard level. Now let's start. Adjust the sputter current to about 12 milliamp. The working mechanism is like this. The chamber is filled with argon gas. When high voltage is applied, the gas molecules will be ionized and accelerated to bomb the platinum target, and platinum atoms will be splashed out to the FTO glass. Here is a SEM image showing the morphology of platinum nanoparticles on the surface of FTO glass. The small bright points are platinum nanoparticles, and the rough surface background is FTO. Here I'm going to prepare 2 cups of different solution. One is ethanol, this one, and the other one is acetonitrile. After long night, let's see how is the titanium dioxide film. We fetch it out with tweezer. And I'm going to wash it with ethanol and acetonitrile sequentially. You can see that the dyes are loaded onto the titanium dioxide network. The other one. Repeat the same procedure. Wash it with ethanol and acetonitrile sequentially. Put the dye solution back and remove the true solution. Then I'm going to use the counter electrode and paraffin to do the sealing. This is a paraffin with a hole in the middle. and the perfume will make a space for the electrolyte. Attach the perfume to the FTO. And here is the contact electrode we prepared earlier. It has two holes. Find the right position. Then I'm going to use the electric soldering iron to heat up perfume, so that the assembly of the DSSC is accomplished. Okay. Then we'll do the electrolyte injection. Here's the electrolyte composed of iodine and iodine 3. Electrolyte will inject into the space between the two FTO glass by the hose. Then I'm going to use tape to seal the hole to prevent leakage. Okay, here is our DSSC. Okay, here we are going to test the solar cell. I'm going to put the solar cell under the solar simulator. The solar cell is connected to a source meter, and the source meter is connected to the computer. Turn on the light. Here is the controller. Measuring solar cell performance is done by scanning and apply voltage across the solar cell and measure the current response of the solar cell. And then we will get a curve, which is the current plotted against the applied voltage. So here we start the scan. As you can see, the current is relatively unchanged at the initial stage. And then the current starts to fall very rapidly. Okay, now the scan has been completed. I'm going to use origin to open the data. And delete the 3 column. And this is the current. The first column is the voltage, the second column is the current. I'm use the first column to calculate the current density. And then I'm going to use the fourth column to calculate the power conversion efficiency, which is short for PCE. The PCE is calculated by multiply the voltage and current density, and then divided by the solar light's power intensity. And then we sort the column in a discrete way. The PCE is about 4. I'm going to use column 1 and 3 to plot current density versus the voltage. The y-axis is the current density and the x-axis is the voltage. Just a little bit. VOC is the crossover point of the curve to the x-axis, and the short circuit current JISC is the crossover point of the curve to the y-axis. The open circuit voltage of the solar cell is the maximum voltage that the solar cell will supply. In other words, that is the voltage without any load applied. And the short circuit current of a solar cell is the maximum current under a zero resistance load. In other words, it is a free flow or zero voltage potential drop across the cell. And now I'm going to measure the solar cell performance in dark condition. Okay, we start. Again, I'm going to use the origin to open the data and draw the curve. Okay. Here we get the JV curve in dark condition. We can see the solar cell in the dark is a large flash diode. A simple dark IV measurement produces the exponential curve, which is a characteristic of diode. And then we are going to measure the IPCE, which is incident photon to current efficiency. Here is the instrument. First we connect the solar cell to the system. Here we put the solar cell under the laser point. When we begin to scan, the wavelength of the laser will change from 300 nanometers to 800 nanometers. Okay, we begin to scan. Get the data and save the data. Later on, we will also open the data with origin. Oops, wrong software. This one. Open the data. And plot the curve. IPCE is a measure how efficiently the device converts the instant light into electricity at a given wavelength. The principle of it is based on illuminating the sample by a monochromatic light and recording the device electrical current. By varying the wavelength of the lights, we get the curve of the currents as a function of the wavelength. And the area under the curve will then represent the total number of carriers created by the device under the light, the full spectrum lights. Then we go outdoors to test the VOC of the solar cell.
可以啊。
So the VOC is about 0.6 under ambient sunlight. That's all for the fabrication of DSSC. I hope you enjoy the process. Thank you.